Hey everybody, in this AP Chem series video we're going to be taking a look at base molecular structure and strength. So we've already seen that strong bases have very large Kb values and produce lots of hydroxide ions and conjugate acid, represented here with BH+. As the strength of a base decreases, the Kb value gets much lower and you make much smaller amounts of hydroxide ions and conjugate acid. For this video, you're also going to have to remember the trend in electronegativity values shown here. So let's start off by clarifying what exactly bases are. They're a little bit confusing in that there's kind of some different types that are out there. The most common strong bases are alkali and alkaline earth metal hydroxides that look like this: lithium hydroxide, sodium hydroxide, potassium, calcium, barium, or strontium, to list just a few. As you look around online or in different textbooks, you'll see some different ones added to this list, but pretty much when a base looks like that, it is going to be considered a strong base. The best way to explain these guys is using a simple dissociation according to the Arrhenius theory. If we do that for lithium hydroxide, the way you would explain why this would produce a basic solution is simply by showing the dissociation of lithium ions from hydroxide ions. Of course, in that solution, you're producing hydroxide ions, so the solution becomes basic. For weaker bases, you're going to expect to see anions in molecules containing nitrogen. Some examples would be the anion called carbonate. NH3 is a very common nitrogen-containing base called ammonia, and then another class of compounds containing an NH2 group. These are known as amines. In all of these cases, if you added them into water, they're going to have the ability to do what a base does and gain a proton, accept an H+ from the H2O molecules. So for the carbonate ion, it's going to look like this. For ammonia, the hydrogen attaches to the nitrogen, and anytime you have an amine, the hydrogen attaches to the nitrogen in the molecule. This of course gives me the products of each reaction. Notice in each example we are producing hydroxide ions that make this solution basic, as well as a different conjugate acid. These descriptions make up some of the key ideas for this video, so make sure to pause and take some time to write those down. We also need to clarify a little bit about how bases actually work. So in most cases, that hydroxide ion is going to be attracted to a lone pair that exists within the molecule of the base. A good example of that is our nitrogen-containing base, ammonia. You can see it has a lone pair on the nitrogen, so my H+ ion is going to be attracted and attached to that lone pair. The lone pair becomes a covalent bond that holds the hydrogen attached as we produce our conjugate acid, NH4+. So this is what's happening when you write out the hydrolysis reaction for a base in water. That H+ that it's gaining from the H2O is attaching to a lone pair on the base molecule. And finally, we can get to how a base's molecular structure impacts its strength. A base's strength is determined by two things. Number one is how easily does its lone pair attract H+ ions. It's also controlled by the stability of the conjugate acid that's produced. So one thing you're going to look for is if your base contains highly electronegative atoms. If it does, that's going to have an electron withdrawing effect from the lone pair that is in the molecule. Because that lone pair has had electrons withdrawn from it, it's going to be less attractive to any positive ions out there, like the H+, and this means the base will be weaker. Of course, the opposite is true. If you've got a low electronegativity atom, that's going to result in a stronger base. You could also look at this from the perspective of stability. That highly electronegative atom will stabilize the base while destabilizing the conjugate acid. This means, of course, that less conjugate acid is going to be forming, also leading to a weaker base. The opposite being true for low electronegativity atoms are going to end in a stronger base. Those are some more key ideas for this video. Make sure to pause and take some time and write them down too. So let's close it out with an example. I've got some chemical structures for some weak bases shown here, and we're going to rank them from strongest to weakest. If you start analyzing these structures, you'll notice that they're all pretty much exactly the same except for one atom, the hydrogen, the iodine, and the bromine. And the key here are the different electronegativities of those atoms and the effect that that has. So the bromine is the most electronegative out of the list. That means it withdraws electrons more strongly than iodine and hydrogen will, which makes that O- less attractive to any H pluses floating around. That's going to make this the weakest base on the list. And for the same but opposite reason, the one with hydrogen will be the strongest base. You could also explain this in terms of stability. If you wrote out the hydrolysis reaction, the base form that contains bromine is going to be more stable because of that electronegativity, while the conjugate acid will be less stable, so you will produce less of the products for that particular base, and hence it is weaker. That also wraps it up for this video on base strength and molecular structure. Thanks a lot for watching, and here is a brief summary.